Okay, so, well, it's a great pleasure. Welcome, everyone. It's a great pleasure to have today Alexandre Gaudillière from the Université Aix-Marseille. And he will speak about using Kirchhoff's forests for network immunization.
Yes.
Thank you very much, Alex.
Thank you for the organization. So, okay. So, as Claudio said, it's about Kirchhoff forests and network immunization. And this is about some work we are doing this year with Luca Avena from Leiden, Michael Emmerich, and okay, it works, no?
Yes.
Okay, and Irina Gurewitsch. Okay, Luca is in Leiden, and Michael and Irina, I don't know actually where they are now, but all these people met in Leiden. So the problem is following: you start from a graph, say with n nodes. And you take k smaller than n, and it does not work. Okay, take k smaller than n, and you should think of that as a small. You can think of that as a small fraction of f of n. Okay, it's a small number. And the question I want to consider is which k nodes should I remove or if you prefer isolate or else immunize to make the network more resistant to epidemic propagation. So this is a question I want to deal with today. Of course, this is a question that received some attention during the last year. But maybe the first thing I should say is that what I will say is of essentially no use for dealing with the current epidemic, because if you think in terms of isolation, what you should do is to isolate infected people and independently of where they are in the network. And if you think in terms of immunization or vaccination, probably you are thinking on a time scale which is already too late for too many people. But however, for what I will discuss today, both things will be equivalent in a simple mathematical setting, which is based on the contact process. Okay, so let's say that eta x is the state of the node x, one for infected, and 0 if not, for each X in the node set, which will be big X. And the model is such that an infected node is cured at rate delta, and it is infected, goes from 0 to 1 at a rate which is a sum on all the neighbor of X of eta X. So I count only the infected people around, eta Y. I count only the infected people around X times WYX, where WYX is the infection rate from Y to X. And so I'm working with a weighted graph, and for each X and Y, I will have a weight WXY. And for today, I will assume that weights are symmetric. So the first thing I need to make precise is to build a notion of resistance to discuss quantitatively this problem. This is based on simple lemma. Eta, so my contact process, is dominated by a branching process I will call it zeta, the critical killing rate of which is the largest eigenvalue we call it lambda of W, and W is the rate matrix. So this is a matrix with a 0 on the diagonal, and the weight WXY in the line Y and column X. Sorry, contrary. Line X and column Y. Okay, so what is this branching process I have in mind? So my process zeta, instead of having in each vertex X value in 0, 1 as any integer value, non-negative, for all X in the network. And if I have zeta particle, let's say, inside X, then at rate delta, the same rate for the death rate of the infection in the contact process. Remember, delta was the death rate in the contact process. Rate delta, a decrease of 1 unit, only if it's positive. And zeta goes to zeta plus 1 at rate the sum on all neighbors of X of zeta Y times WYX. So and there are many people in the neighbor of X. Each of them can give birth to a new guy in X, and each guy at rate WYX, and each guy is killed at rate delta. It's a elementary algebra to prove that if delta...
Excuse me.
Yes.
So the W takes value 0 or 1 or something like this?
No, W is any non-negative weight. It's W like weight, and it's any rate.
No, it's not possible. You assume that zeta takes positive integers values.
Ah, sorry. Yes, this. At this rate, so this is a rate, you have one more guy in site X, and zeta is a number of guys inside X. So if zeta of X is zeta, then this will decrease at rate delta, and this increase of 1 unit at this rate.
Yeah, but Alex, it doesn't mean that each one disappears with rate delta, because otherwise it will be at rate delta Z that you go from Z to Z minus 1.
Oh, okay, sorry. Yeah, of course, delta Z.
Oh, okay.
Sorry. Yeah. Delta zeta of X. Okay. It's clear.
Okay, now it's clear.
Thank you. Okay. So the domination of one process by the other one is the basic coupling you can build between these two processes. And as far as the branching process, this one is concerned, it's elementary algebra to prove that if delta is larger than lambda, the largest eigenvalue of W, then this branching process will be subcritical. It will disappear exponentially fast. And as a consequence, for delta smaller than lambda, the epidemic, since it is dominated by branch process, will disappear. Exponentially fast. Okay, so because of this, we choose lambda as a vulnerability measure of the network. And actually, so this is only in this direction that you have this clean statement, but this upper bound for a kind of critical value for the contact process is not so bad if you think that the critical branching process could look like a simple random walk. In this case, it would take only value in 0 and 1, and the part which is above the infection process is not so important. But I will not discuss that. I just say that because of this result, I have this is clear, and I take lambda as a vulnerability measure. So in this context, the problem
I didn't understand, Alex. Yes. You mean that you don't know if delta is larger than lambda, if the process will survive forever?
No, that I don't know. Okay. And no, I know that it will not survive forever because it's finite graph.
Okay, sure.
So it will disappear. But I don't know if it is larger than delta, then the time it will need to disappear is exponentially large in the number of nodes. This kind of things I don't know.
Okay.
Okay. But for sure, if delta is smaller than lambda, then it will disappear exponentially fast. Clear?
Yes. Thanks.
Okay. But probably it's not so wrong to think that if delta is larger than lambda, it will last much longer. But I'm not proving something like that. I do not discuss this. Okay.
Excuse me, Alexandre, you are not making any assumptions on the initial graph?
Finite graph.
That's all.
Connected.
No, yes, you need something like connected, something like this, I guess.
Yes.
Okay, thank you.
Okay. So the problem I want to look at now, because of this context and this observation, is to find S, a subset of the nodes, such that with lambda S, the largest eigenvalue of WR, and this is my notation to say that I consider the matrix W restricted to the X and Y only in R, where R is the complementary of S. So S is a set I remove and R is a set I keep. So I'm looking for this set S such that the eigendrop which is defined as lambda, the maximum eigenvalue of my original graph minus lambda S, the maximal eigenvalue of the reduced graph is as large as possible. Of course, and this set S, as I said at the beginning, is with the constraint that it says its size is k. So I fix k smaller than n, and I want to fix the size of k set S so that the eigendrop, which is this quantity, is as large as possible. Is the problem clear?
Yes, thanks.
Okay. One reference in the state of art of this problem is called the net shield algorithm, and I will explain the heuristic and the algorithm to face this problem. And this is from 2016, and many people are involved here. So I just give the last name. So it is Chen, Tong, Prakash, Tsuakakis, Eliassi Rad, and Chao. Okay, what is first the heuristic? So you are interested in the eigendrop lambda minus lambda S. So by definition, it is the largest eigenvalue of W that you can write as something like transpose of some ground state psi W psi. I said ground state if I think of W as the opposite of some Hamiltonian, but it's L2 normalized, so the largest eigenvector of W. The eigenvector associated with the largest eigenvalue minus the same thing for the restriction of W to R, and let me call psi R the eigenvector associated with this largest eigenvalue of the reduced graph. So here is a heuristic. Because K is small, the heuristic says that WR here is a small perturbation of W. And in this case, psi R won't be very different from psi. And you can even take it just at the restriction of psi to R. So assume this is true. This is heuristic. You can discuss this, but this is how computation is done. So this you can discuss, but we say it works like this. It's more or less the restriction to R of psi transpose times this times that. So psi R was by definition the largest eigenvector, and this is the restriction of the largest eigenvector of the original graph. Now, next line is the exact computation. This is again elementary algebra. This is equal to 2 lambda. This is the largest eigenvalue, the critical killing rate of the branching process, times the restriction of psi to S. Remember that S is a complementary of R square minus the restriction of psi to S times D times the restriction of psi to S, where you write W, the rate matrix, as a block matrix A, B, C, D, and this block index R and this block index S. So remember that S is so first thing, this quantity is defined as the shield value. This is definition. Shield value of S, which you can, I will write it SV, like shield value of S. And one thing which is interesting is that SV of S has a computational cost of order K2. So remember that K is small. You don't want to isolate many people. And for a given S, the computation of the associated shield value is just a K by K computation, so a K square. It's fast. Okay. Based on this, which is the heuristic, the algorithm works like that. You use a greedy algorithm to maximize SV of S, the shield value of S, after computing psi and lambda. So first point, you compute psi and lambda. This is just the largest one eigenvector. You use power method to do that. It is a kind of standard computation. And then you compute S by adding nodes one by one. each time maximizing the shield value increment. Okay, so this is definition of shield value. Beginning S is empty. So first thing you have to do, because this has diagonal 0. Remember, this is the diagonal is a diagonal of V, which is 0. So essentially, you start with the node where the ground state concentrates. And you remove this node, and then you choose the next node that will maximize this quantity, and so on. Is the algorithm clear?
Yes. Yes.
Okay. So this is called net shield.
Excuse me, something I don't understand. How do you start with the empty set?
Yes.
Mm-hmm.
S is at the beginning an empty set, and then you choose the node that maximizes this quantity of set of size 1. Mm-hmm. So this is just where psi concentrates, the node where you have the mode of the ground state. This is pre-computed. And then you choose the next node to add among the n-1 possible that will maximize this quantity, but this is fast to compute because it is at the end, it is only at worst k by k computation. And you can do this in clever way, and this gives you some set, and you said, and NetShield said, this set is a set of nodes of size k when you have k nodes that you should remove. Clear?
Mm-hmm. Yes, thank you.
Okay. Now, we want to discuss the use for this problem of random forests. The random forests are built with Wilson's algorithm that probably many of you knows, but I will remember it. So it works like this. This is your graph X. You are given a positive parameter Q. You choose some node, any node in X, and you run the continuous time Markov chain on X. So first thing, you wait for the first jump time, then you jump somewhere. You wait, you jump, you jump, you jump, you jump. When you make a loop, you erase the loop. So you just have this. You make a loop, you erase the loop, and you continue like that up to sometimes. Something else that can happen is that you go like this and you go back to your starting point. Then in a new loop, you erase the loop, the whole loop, and you continue. Sorry. And at some point, make no loop anymore. You stop at subtime tq, which is distributed as an exponential of parameter q. Okay. Then you take another node and you do the same. For another independent time tq. From the
sorry, take a node which doesn't belong to the path you already constructed.
Yes, because from this point, from second point, there is a new rule. It is that if you run into something that you already built, you stop without waiting time tq. So doing this, okay, you have oriented paths that are oriented towards the point, the big point here, where you were killed. It's possible that you have isolate point, because if you start from here, you make a loop and you erase it and you are killed before going away, you will have isolate point. But when you have exhausted all the point of X, what you get is a rooted forest with this point that are the root of the forest phi. Let me call phi q, if it's a random variable. That depends on q. So set of root is this. And theorem, which is due to Wilson in 96, that the probability that your random forest is a given forest phi, this is proportional to q to the number of root, which is the same that the number of trees in your random forest, times the product on all edges you have in the forest. You can see your forest phi as a union of different edges times the weight of each of these edges. And this you call W of phi. Okay, this is Wilson's theorem.
Alexandre, excuse me, I'm afraid that I didn't get why you use Q in your definition.
Q is the time when you kill the first random walk. You make loop erase random walk up till time TQ. TQ is an exponential of parameter Q. Okay.
So you start making a pass. When you get a loop, you erase it, and then you do it again until the time T of Q occurs, and then you stop it.
Yes.
So and you start counting. You start the random time every time you start again.
Except when you start it every time you build a new path, but you don't wait it if you run into some already built path.
What you do then?
You stop here. So again, if you have a first loop erase path like this, and then your second starting point this, and you make some paths like that, you erase the loop, and then before time TQ, you run into what you already have, then you stop without waiting TQ.
Okay, thank you very much. Thank you.
This is Wilson algorithm. And the weight of forest phi is this, because the probability is proportional to this quantity. So there are two proofs of Wilson theorem. One, of course, is of 96, is the Wilson proof, but there are also another proof, which is very, very elegant, that starts by proving that the order of starting points has no influence in the final object, in the law of the final object. That's first point. But there are different proofs, so I call it proof 2, which is due to Marshall in 2000. With the simple direct proof, which is you compute the law of the loop erase random walk. And then once you have the law of the loop erase random walk, you can just concatenate the different probability, and you make exact computation just using the law of the loop erase random walk, and you see that probability of phi q is phi is the quantity I said, q to the number of roots, times the weight of phi, which is the product of all the weight in the forest, divided by some quantities that you see appearing here. And you have an explicit value for this quantity, which is normally a partition function of this weight. Wilson proof just proves that the probability of having phi is proportional to this, but it does not compute partition function. So you have explicit computation, and a corollary of this computation is actually a theorem by Kirchhoff of 1847, said that z of q, which by definition is a partition function, so it is the sum on all phi of q to the number of roots times w of phi, product of all edges in phi of the rate. This is exactly equal to the characteristic polynomial of the generator of your random walk with L, which is W, the rate matrix, minus, remember that W at diagonal on at 0 on the diagonal, minus Wx, where Wx is the rate of your holding time before jumping. This is the sum on all y connected to x, w, x, y for x in x. Okay. This is one, in my opinion, one of the most beautiful formulae in combinatorial and algebra, and this computation of Marshall is probabilistic proof of this result. Okay, now these are the random forest we want to use. If you take q equals to 1 and all the weights that are 1, this is a uniform rooted spanning forest. And in our community, often people talk of this, even in this generalized case, of the uniform spanning rooted forest. But when you talk with applied people, this is very, very confusing to call this uniform distribution of all forests. So I prefer, because of this result here, to call it Kirchhoff forest. So Kirchhoff forest is this. This is random object with this weight. Okay, why do we want to use it for the problem I want to discuss today? Because if you write X as R union S, remember that S is a set you want to remove and R is a set you want to keep. Turns out that rho phi q is a good candidate for R. Because what you want in the point you keep in your graph is that there are far apart points. They have difficulty to infect each other, and they're also well distributed in the graph. And there are many properties of this forest that you can use to make this kind of statement precise. But the statement I prefer to use today is the following. If you set RQ, you call this the set of root, shorthand, and you call W RQ of XY for XY in RQ, the rates of the trace process on RQ. So
the problem is that you don't control this number.
So you control it with Q. For large Q, you will have many roots, and for small Q, you will have a small number of roots, and you can adjust it to have a complementary size of the root, which is of size K. So it corresponds to large Q if K is small.
Okay,
okay?
I agree, but it's a random number, and you want
number, but okay. There is an issue to sample exactly forests with K node, with n minus K node, n minus K root, but you can do it in many ways. One is to recurrently adjust the value of Q to fluctuate around the wanted number, and there is standard procedure to do that, and wait for having the correct number, and it will be quite fast, but you can do even better, but I don't want to enter in the details to sample this conditional size, because I prefer to discuss other things. I agree with you that there is an issue for having exactly n minus K roots, but you can do it. Okay.
Alexandre, I'm sorry. You how many starting points for the forest you take? You decided. So you can start doing it until you complete all the points. Is that,
yes.
That's what you complete all the points.
Yes.
Okay. Thank you.
So for large Q, this will be linear in the size of the graph.
The number of roots.
The number of operations you will have to do to obtain your root set.
Okay. Okay.
Okay. And as I said, there are many justifications to try this set as a set of set node to keep, and one is this result, which is quantitative. This is a theorem we made a few years ago with also Fabienne Castel and Clotilde Mello from Marseille. So you take any K between 0 and smaller than n, and you look at the expected value of the mean value of the jumping rate for the trace process. Yes, I was saying what was the trace process. So okay, trace process. What is trace process? So you have a set X, a set R, and assume that you have a random walk that starts in R and that move in your domain X. Then the trace process is a random path, the random trajectory you get in R. So this part here. This is Markov. This is associated with a generator. This is a generator of the trace process. I denote by WR or RQ the rate of this trace process. So this WRQ of X is like before. It is the sum on all Y in RQ minus X of the rate of jumping from X to Y. So if you want this quantity,
So you consider random walk with rate WXY. And then WR is the trace of this random walk on R.
Yes.
So it's the random walk.
Yes. Is it clear? Or there's a question?
Now it's clear.
Okay. So R is random because it is a set of roots. And I consider the trace of the original random walk on this subset of the original process. And now I look at the jump rate of the trace process, and I look at the mean jump rate on this random subset. If I condition this to be exactly n minus k, this is what I want, to remove k nodes, then I have exact formulae. This k plus 1 divided by a minus k times bk plus 1 divided by bk, where b are the coefficient of the characteristic polynomial. So this I want to write it as sum for k equals to 0 to n of bk times q n minus k. Of course, it's a polynomial in q. Bk I call the coefficient, and you have exact formulae of this mean jump rate. Okay. Now, why is it important? Something which is important is that the contact process with rate WR will dominate that with rate matrix WR. So the restriction you are interested with in. So of course a good point. This is the node infection rate. This is a good point to have a low mean infection rate if you want a system which is resistant, a network which is resistant. And you will have an upper bound with of this mean infection rate for the reduced network. And this quantity is decreasing with k. So let me call this quantity alpha k. So remark, alpha k divided by alpha k minus 1. This is smaller than 1. This is what I said. It is decreasing. So alpha k depends only on the coefficient of the, maybe I will, okay. Depends only on the coefficient of the polynomial up to some factors which is explicit in n and k. And saying this is actually equivalent to Newton inequality. This is some relation between coefficient of polynomial with positive or negative roots, which is our case here. So this is smaller than 1, and it's decreasing. Actually, it is strictly decreasing. You can prove that it is this quantity, 1 minus something. For this, so without this minus is exactly Newton inequality. And to get these extra factors that prove it is strictly decreasing, you just need to observe that Bn is 0. Bn is the lowest degree coefficient, and since you have 0 in the eigenvalue of the generator, you have Bn equals 0, and if you use that also, you get this. Newton equality plus this is equivalent. And actually, you have equality for the worst case. And the worst case is the case of complete graph. And when you move away from the complete graph, you will have a more dishomogeneous in the spectrum of L. The stronger is the decay. So when you select in this way when you select in this way the nodes, you will have a strong decay. We'll have a strong decay of the mean infection rate for the trace process, and as a consequence for the reduced network. Okay, so this is the idea of using this Kirchhoff forest, and I will give you one example of how it works to make it into an algorithm, skipping the questions the issues that Claudio raised about sampling exactly k-nodes, but believe me, it's doable.
Alex, can you do that in 5 minutes?
Yes, I will do that in 5 minutes. So I just need to share something else. Okay. So this is just one example. I have much more example, but I just give you this one to explain how the algorithm works. The main theorem I gave you is this one, and now I give you the example. So this is an example on a conference graph. Conference graph. It's also about conference in network studies made in 2009 in Torino, where researchers built their own graph that have magnetic badges, and where they were close together 10 years ago. The time they spent together was registered, and so you have 3 days. So conference 3 is for the 3rd days of the conference, and you have on this 3rd day 97 participants, and the number of edges, connection between people. So you have a connection if you spend some time together in the conference is this number. And the largest node rate is the larger WX in this graph. Each edge is weighted by the time it was the guy spent with the other one. The initial critical rate is this one. If you use Netshi algorithm to remove 12 nodes, then this is the set of nodes for this graph you get, and it works quite well. This is the eigendrop. ED is for eigendrop. So you have at the beginning critical rate set, which is 1,100 or 200, and you decrease by 1,000. So you reduce by essentially 10%, or you reduce by 90%, and you get only 10% of the initial rate. If you use one Kirchhoff forest, this is the result we get. We have a smaller eigendrop, and but this is a random thing. We just sample one forest. So the idea is to use more forests. We sample, in this example, 50 forests, and the 50 is in such a way that the time we need to make all the computation is the same that we will have using just net shield algorithm. And among these 51 forests, we look at the root set, and we can compute for each root set or complementary root sets, the same, the probability of getting exactly this one, and we select the most probable. And what we get is something which is already better. But we can also make other things, like, for example, because the shield value is an approximation of the eigendrop, we can select among these 51 Kirchhoff tries the one with the larger shield value. And this is the thing we get. This is worst, and it is also worse than net shield. But shield value was built as I explained to you as some heuristic of what is the eigendrop of a given set, and you can a bit adjust this heuristic and make a slightly more accurate computation, and select among the adjusted shield values the one with the best adjusted shield value. And then you get with the forest with a better eigendrop. Something else you can do is that this is the last thing, you can select among all the forests you get the one that will also lead you to the best rate drop to remove the maximal weight of all edges in the sample forest. And doing that, we get something which is better than all the previous forests. And so with this different way of sampling many forests, we have 5 ways to look at one in particular at low cost. And in these 3 or 4 forests, we select the best one. And this gives you a combined algorithm, which gives you to this number for this example, which is better than the original one you had with the net shield, which was 1,000. Okay, this is just one example. I have no time to show you the whole statistics. It would be more to say and more to discuss. There are some cases in which it is better, but I have no time to explain now, to use the forest better than net shield. In some cases, with net shield is better than the forest. But my main message was that among a natural object, you have a natural weight based on the net shield ID to select what should be the best forest efficiently, and among a few forests, compute what is the eigendrop and choose the best one. That's what we have done. And in some cases, this gives better results that what was obtained previously. And this was based on this nice property of Kirchhoff forest. Thank you.
Well, thank you very much. I think we can unmute our microphones and thank Alex for this very nice talk. So thank you, Alex. And now we are open for questions.
I asked a lot of questions, but I could ask you to give some reference of your work on this. I'd like to know more. It was a very interesting. I'm very interested.
So the first reference is a net shield paper. For this work, we will publish. We will put it on archive in a few weeks. It will be with much more comparison on statistics. I had no time to show you this statistics, and you don't have to think that it is better in all cases than what is already done. It is in some cases we can improve some things. That's it. And you will have soon the reference.
Thank you.
And then, Alex, you're talking about complexity, algorithmic complexity.
Yes.
So
Yes.
your method requires to compute these BNs, these coefficients.
No.
Okay. So I misunderstood.
No, this is a property of the forest. The method requires to sample root, and then for this root, estimate what is the eigendrop. And this is independent of this coefficient. The heuristic for why the forest was useful is based on this property, which is related with the BN.
Okay.
But you don't need to compute the BN. And essentially, for one forest, you do all the job in linear time, and to be in the same order of what is already done with NetShield. Remember that NetShield had to compute one eigenvalue that we don't need to do. We have the right to use a few forests, and among these few forests, just select in an efficient way without computing eigenvalue what should be the most efficient one, and then compute effectively eigendrop to check if it's better or not. Okay,
and this is made on time proportional to the number of nodes.
For one forest, it is proportional to the number of nodes. And for, in this case, I said 51 forests. This is proportional to the number of edges.
Okay.
The 51 comes from here. You choose the number of forests to have something which is proportional to the number of edges. Time some correction, but essentially this is this. The reason for this number of edges, it is because if you want to compute effective eigendrop, then you need to compute the largest eigenvalue. And in many cases, this is like the number of edges.
Okay, thank you. Any other question?
So Alex, so this tree is only organized, is self-organized in some sense. Yes. How do you get those most probably nodes?
Okay.
I don't understand the idea of why the nodes that you erase are the best, the worst or the best.
Okay, so I go back to Blackboard. Can you see my Blackboard?
Yes.
Okay. Okay. What is the probability? So you have actually we have three ways to select a forest among a bunch of forests. 3 ways to select one forest among a few samples. So as I explained before, the number of samples is done in such a way that you are competitive with what people do in running time. So what is the probability that your set of roots is exactly some R? So some given R. So this is random variable, and this is a fixed subset. So by definition, this is 1 over partition function of the sum of all R, of all forest phi that have root sets exactly R of the weight of the forest times Q to R. And that's it. Do you agree with this formula?
Yes, yes. So the weight of the forest is
yes.
Oh, okay.
Now you go to Kirchhoff theorem. Kirchhoff theorem said that below what you have is the characteristic polynomial of the generator. Okay. And reasoning exactly in the same way, remember that this is the sum of all forests. If you make this restriction, what you get is exactly the determinant of okay, sorry. So first, there is a Q to the R that goes outside. And then you have the sum on all forests. And using Kirchhoff theorem, what you prove it is that it is the determinant of the opposite of your Laplacian reduced to the complementary of R. Okay, so this is constant that does not depend on R if R has a fixed size. So the weight is that one, and X minus R is a small set. So you have just to compute a determinant of your Laplacian on a very, very small set. So this is cheap, and you can you can select among your, this example 51 or 54, I don't remember, forest, the one with the best determinant reduced to the root, to the complementary of root. So this is one way to select forest. And we have two other ways. One is to use the shield value or the adjusted one. And the third one is to measure among all your sample forest, how much edge weight you will remove from the graph. Because in all these things of largest eigenvalue, you always have a domination by the largest degree of the largest rate of the largest node rate. And so this you want to decrease, and the most efficient way to make this decrease is to remove a lot of mass from the edges. And this is the third way to select. And actually this third way is the most efficient one. The computation is even cheaper than this one, and the results are better. For showing this, I need to. No,
I think it's okay. I think
show more statistics, and if you want, I can do it, but I'm not sure I have time to do it. Claudio?
No, it's okay.
No.
I can do my homework, don't worry.
Okay.
Thank you very much.
Welcome.
Any other question? Well, if not,
if you have time,
I want to.
Sure.
Question. No, it's just a single question, Alex. You said several times about statistics. What do you mean by statistics here?
Okay. I show you. This.
Okay, very nice. But what is this?
Okay, so these are example of many graphs. The conference day is that one that I show you, and the airport networks, famous karate club, Taurus, and where we made many tries of 100 tries for different value of k. K is this fourth column. Here we have number of edge, number of nodes, number of edge, and in this column, what you see is essentially the percentage for which NetShield did not give gave the best result. So in many cases, NetShield is already very good, but there are some cases, especially when you want to immunize a small fraction, a true fraction, and not only 2 nodes or 5 nodes of the population, where the forest, you see, it's much better. And and usually what you see is that it works better in many cases. It works better by selecting the largest edge, the removal, rather than trying to guess the eigendrop using the shield value heuristic. And the conclusion, when you look at deeply in this data, is that there are two cases when it's really useful to use the forest. One is that when it is too costly to compute the eigenvector, because this has some cost, and sometimes you just can't do it, even if it's just one vector. And second, if you want when you go deep in the analysis of net shield algorithm, what you see is that even though the heuristic is global, because it looks at the eigenvalue of the whole matrix, it is actually a very local algorithm, because the ground state is usually very, very well concentrated, and essentially what it does is that it kills the point where the largest part of the mass is concentrated on this ground state. And if you want, using net shield, what you will do is that you will have a strategy of vaccination, if you want to make vaccination, in which what you want to do is to suppress the most terrific potential reservoir in the epidemic. But if what you want to do is to allow this reservoir and protect the rest of the population, because there will be some reservoir somewhere, then in many cases you see from the statistics that it could be much better to use the forest.
Thank you. Okay. Thank you. Thank you.
You wanted to add something, Alex?
Yes. But already I said it, because the example I gave at the end of the talk was one example where we could improve something. But I just wanted to mention that in many cases already with the net shield it works very well, and there are specific cases in which this is relevant. But this has to be developed in a further discussion.
Well, so I think we can unmute again and thank Alex for this very nice talk.
Thank you.
Thank you very much. It has been great.
Then before we close this session, let me remind you that we continue next week with Mariana Huskik from the MIT at the same time. So thank you all and see you next week. So bye-bye.
Bye.
Bye.